Season 3, Episode 2, Habitats in the Void. And welcome back to another edition of the s3e2 podcast. My name is Chris Stewart and I'm sitting, as ever, around the round table in her office. Dr. Emily Brunsden, how are you doing?
I'm very well, thank you.
Good. Season 3, Episode 2.
Yes.
We're on alien life.
Yes.
Life in the universe that isn't us, which we've never found. I mean, I think we need to be clear about that at the beginning of every episode. We've never found anything outside of our own planet.
No.
But
except for ourselves.
It doesn't. Well, yes. I mean, sometimes we have. Isn't that a weird idea that there are these photographs from people from in space looking back at the Earth, and they're the only ones who aren't there? It's just that's one of those weird feelings. It's like, oh, that must actually feel very, very strange.
That's everybody in that photo except me.
Yeah, everyone who's ever lived. Like, not just everyone who's alive now. Anyone who's ever lived except me. Well, and my colleagues.
And that person's ashes that they put on the moon.
Well, that too. Yeah. Did they do that?
Yeah.
Whose ashes did they put on the moon?
Oh, someone very wealthy, I assume.
Yeah, probably. Yeah, other than them. It's a small asterisk next to a profound moment. Anyway. Look, that's besides the point. In this series, we are looking at life in the universe other than us.
Yeah.
And in the first episode, where did we get to, Emily?
We started off with my favourite topic of discussion, which is stars.
Stars, yep. Because if you're going to have life, you need a planet. And if you're going to have a planet, you need a star.
Yep.
That's where we began.
Yep.
Yeah.
Starts with stars.
Yeah. And it felt a little bit to me like we were just whittling it down to the point where basically we said, no, it's just us. But we pulled back from that deep, nosedive, that narrative nosedive, and came to the conclusion that there is a possibility that maybe there might be other stars that might have other planets which might have life. So let's just continue going with that. Emily, what are we talking about today?
So we're talking about exoplanets, and it just so happens that today, which is the 6th of October,
yes,
is actually a really important anniversary for
6th of
exoplanets.
October. Okay, is it the anniversary of what, like the first one?
Well, pretty much.
Yeah.
It's the first, I'm not going to say proper because that's a bit mean, but 30 years
Not
ago.
throwing shade to the other ones.
Today we found, or the announcement was made about the very first planet that we found around a sun-like star.
Oh, okay. And as we have found from last week's episode, that's actually fairly important.
It's incredibly important because the very first exoplanets were found around these weird things called pulsars, and that was all very strange and we didn't really know what we were looking at.
I don't think you want to be around a pulsar.
No,
do you?
no, it's not a good idea.
Not a good place.
No.
Yeah.
So parking those weird ones aside,
Yeah.
first exoplanet found around a sun-like star. And 30 years ago.
Wow. Does that make you feel old? That makes me feel old.
Yeah, but wow, just think about how far we've come in 30 years.
30 years ago, I was in university, which does make me feel
Do you remember
very
the
old.
announcement?
I don't, because I wasn't paying much attention to astronomical stuff at the time. I was studying theoretical physics, and my head was deeply buried at the other end of the size scale of the universe.
In the
looking
student
at very,
union
very, very
bar,
small
right?
things. And in the student, well, that's what, most of my time. Playing cards. A lot of cards I seem to remember from my undergraduate. Point is, no, I don't remember the announcement. Do you? You would have been somewhat younger.
I was about 10.
Right,
So
yeah.
I was definitely much more excited about things like my Barbie dolls, to be honest.
Hey, look, Barbie could be an exoplanet researcher as well. Why not?
She is, yeah.
Why not? So 30 years, we've had a lot of time to nail this one down, Emily. So after the debacle of episode 1, where we basically said, geez, even if momentarily, no, there are none, it's just us. I'm hoping you're about to tell me that there are loads of planets on which we have a very high likelihood of finding life. Yes? Right.
Well,
good. Okay.
I'll make you feel better. Look, let's look at it this way. So this announcement 30 years ago, which was made by Nobel Prize winners, of course, Michel Mayor and Didier Queloz, they found 51 Peg B. Now, I'm banging on about this one because I think it makes a point that we're just going to have to keep in the back of our minds for the rest of, I guess, forever, but certainly for this episode.
Okay, we'll stick a pin in this one.
So 51 Peg B is called subsequently been named Dimidium.
So it's got a planetary name. That sounds like something out of like Star Wars or Star Trek or something.
Yeah, some exoplanets have names. Yeah, this one's called Dimidium. It's a planet that is about half the mass of Jupiter, that is going around its star at something like 1/8 the orbital distance of the Sun to Mercury.
1/8 the distance to Mercury.
Yeah.
But it's half the size of Jupiter.
Yeah.
Okay. That's a little bit outside the parameters of our solar system.
Well, exactly. And this is the point. So this whole this planet was the very first hot Jupiter, right? Very, very massive gas giant found incredibly close, way too close if we're
that does
quite
feel
honest.
Too close for comfort, to be honest.
To its host star. You know, so it's 1,000 degrees on the day side. It's just... It's bizarre. It's utterly bizarre.
Doesn't feel terribly habitable.
It's not. And I'm not going to try and claim that it is. You'll be pleased to know.
Just to be upfront, we're not putting this one out there as your archetypal, there's going to be little green people running around on here. No. Okay.
But what this planet, I think, does illustrate so wonderfully is that even the very first exoplanet that we found around an ordinary sort of star was weird.
Right.
It was unexpected and it was
setting
weird.
The standard.
Yeah. Basically, our exoplanets don't match our expectations. Because you would assume that, okay, we're, 8 planets going around a sort of fairly ordinary star. If you're going to go out and find the very first other planet that's not in our solar system, you'd kind of look for something similar.
Sure. And you might expect, given our own experience here in our solar system, that surely, just by the law of averages, we're probably going to be not terribly far from normal.
Well, exactly.
Why would we be special? And so if we're looking for something else, it's probably going to look something like us. Turns out not so much.
No, well, exactly. And it turns out to be one of the rarest types of exoplanets as well. So, these, we're not claiming that actually we're the weird ones and all these hot Jupiters are the norm. That's not the case. Hot Jupiters are rare. And we understand a lot more about how they got to where they are because they don't form that close to their stars, thank goodness. But it's just that nice kind of weird quirk. And I think exoplanet science has always been a bit like this. It's always just thrown up kind of almost what you least expect every time you look.
Is that because, I mean, you just said hot Jupiter's fairly rare, but it was the first one we found. And so either that was just a really weird coincidence, or maybe it's some of the rare ones that are the easiest to spot.
It's certainly the latter.
Right.
Yeah. So big planet going around a small, in this case, star has a big effect on the star. And all of our exoplanet techniques pretty much boil down to, can we measure something that's the star's doing that tells us it's got an exoplanet?
Right.
More or less.
Right. So it's a little bit like how elephants are not particularly common in lots of parts of the world, but they're a lot easier to spot than ants, which are very common.
Indeed.
You'll see an elephant from a long way away.
Yeah.
That kind of idea.
Yeah, that's nice.
Yeah,
that's a nice analogy.
There we go.
So I think that's what we just got to keep in mind when we go through the rest of this episode, that exoplanets are weird and they don't always meet what our base expectations might be.
So we'll stick a pin in that, and if we need to come back to, just as a reminder, remember everyone, exoplanets are weird. Okay, so having said that, let's put that planet aside because it's not helpful in our search for life on other planets. So what would be helpful? I mean, look, we've got one planet that we know of that has life on it, and that's us, the Earth. So does it make sense to look for planets that are a bit sort of earthy?
Yeah, well, that's the obvious thing to do, right? Let's just go out into the thousands of exoplanets that we've now found to date.
Yeah, 6, what are we up to now? 6,000, yeah.
And just find the ones that look the most like the Earth.
Are you about to tell me that there's like 3? So please tell me that's not true.
You can read my notes from there, surely. Well, okay. Let's just remind ourselves that defining what habitable means in the context of an exoplanet.
Sure. So we talked about this briefly last time, but let's go into it in more depth.
Yeah, well, defining it's really hard.
Yeah.
Because we've got one example, as you say, of a planet with life. It's the Earth. What parameters of Earth do you say that another planet has to have to be an Earth twin and habitable for life? Does it need to be kind of rough? Almost everyone agrees that it needs to be roughly the same temperature-ish for liquid water. Everybody kind of comes to a consensus that, yeah, water is probably a good thing. Let's go with water.
Okay. And when you say, can I just clarify something? When you talk about water, is this like an astronomical version of water in the same way that metals are a bit different? Like there's hydrogen, helium, and then there's metals. When you say water, do you mean like H2O or do you mean liquid stuff?
Okay, no, I am actually going to disappoint you and say H2O.
Okay. No, that's fine. I just want to know where we are.
It's water's made of metals, if that helps.
It doesn't, actually. But anyway, yes, water. So when we're talking water, actual
Yes,
water
yeah.
as we know it.
Yeah.
Good.
Yeah. Okay, we're not going to talk about space water. That's going to be specifically different.
But why, why water? Why not other stuff?
Well, we know that life on Earth is very intrinsically linked to water. I mean, this is a little bit like what we talked about with light in the last episode. Not every organism, not every species on Earth that is alive uses water necessarily. There are species, things in the deserts that don't really see any water, for example. But by the broad mass, life on Earth seems to really need this water stuff to get along.
Okay.
Now, you can make I'm going to say science fiction arguments about, well, maybe you could do different things. You could use a different liquid. You could use like liquid methane or propane, I don't know, some organic liquid, basically, and achieve the same thing. And I'm not going to say that's wrong, but it's not in the realm of what we understand life to use, at least in our one example. So in a genuine case of just go for the easiest thing first.
Sure. We've come back to this a number of times on this podcast. Sometimes you've got to go and look under the street lamp where the light is.
Yes.
For your lost car keys, even though you know that they're over in the darkness somewhere. Yeah, but I'm looking in the street light because that's where the light is. So let's look for watery stuff.
Yeah, well, I say
earthy.
water because the very first parameter is not actually that water exists. That's kind of that comes down the road if we're very lucky to be able to measure something like an atmosphere or an exoplanet. The very first criteria is really, is it in this habitable zone? You might have heard it called the Goldilocks zone, where liquid water could exist.
Right, and liquid water exists at least at reasonable pressures. It exists between 0 and 100 degrees centigrade, Celsius. Yes.
Yep. So we call this kind of distance. So every star has a distance, whether it's closer in for a cooler star or further out for a hotter star, where that kind of temperature could be expected on an exoplanet.
And that's your Goldilocks zone.
Yeah. And you can wiggle with that a little bit based on what your atmosphere is like, how much heat is trapped by the atmosphere or how thin it is, and therefore how much is lost. We've got examples of both of those in Venus and Mars.
Yeah. So just because you're within the so-called Goldilocks zone doesn't mean that it is just right. It just means that it could be, as opposed to being too close where it's stupidly hot.
Yep.
And you're just going to burn the living daylights out of anything that might be there. Or it's too far away and it's just stupidly cold.
Yep. And everything's frozen.
Yeah. Okay.
So we have this habitable zone. So we're looking for rocky planets then in this habitable zone. Why rocky planets? Well, that's kind of what the Earth is, right? We're this lumpy rock of one Earth mass going around our sun.
But I mean, there's more to it in that than just simply you go with what you know. I mean, if you look at the alternative, what's not a rocky planet? Well, we have some in our solar system. We have Jupiter and Saturn and, other planets like that. And you'd have to ask yourself, what would life be like? How could life be like on those planets? Like, what is Jupiter, Emily?
Well,
like you can't stand on it?
No, it's a big gas giant.
It's a big gas giant. Like how?
Yeah.
What is life going to be?
So at the very basic, and this is an astronomer talking biology, so it's going to be basic level.
If you're a biologist out there listening to this shaking your head, that's fine. Just write to us, but we're going to go with it. Yeah.
Basically, you had some sort of murky, maybe slightly selenic pools at some point in Earth's early history that lightning or something charged happened, and therefore life. I mean, that's the very, very...
yes, ingredients, ... something happened, ... life.
Yeah. But to have that kind of murky, slimy pool of whatever to begin with, that's not going to happen on Jupiter, right? You're caught up in an atmosphere. There's no solid surface. Even the core of Jupiter is very strange and, far too hot and far too high pressure for any liquids to be pooling around and doing things that slimy creatures would like to live in.
Yeah, you're looking at some very speculative ideas in sort of, science fiction theoretical biology in order to come up with something that might work. And again, if you work in that particular area, let us know. We'd love to see a research paper that points us in a different direction. But for the time being, we're going to look at rocky planets.
Yeah. And rocky planets, because there's all sorts of wonderful things that go on with the Earth that help the chemistry and the biochemistry that then follows on from that. So the geothermal activity that goes on in the Earth's crust and how that interacts with both the oceans and the atmosphere. So there's all sorts of processes that are going on. So you kind of need that rocky foundation for all of that to exist on, if you like. So Earth twins, therefore, by this definition, should be small rocky worlds in the habitable zone. We'll just forget about anything to do with the star right now because we've parked that in episode 1.
Sure.
Right?
Okay. Yes, we've already identified that. Look, there are a certain breadth of star types that we should probably just leave alone.
Yeah.
Let's just not even pretend to look at those. We've got some stars, and then now we're looking for. Now you said small rocky planets. Why not big rocky planets? Could you have big rocky? Do they exist?
Yes, they do. We have. Now I think they're called Chthonian planets.
Sounds good. Again,
Chthonian,
does sound very Star Trekian.
Yeah. There's a CTH in there, for example, and these are what we think might be these hot Jupiters, like the one we mentioned at the top of the show. That have had their atmospheres stripped.
Just blown away. Right.
And what you're left with is a solid core, but it's a much denser, bigger solid core than just, say, the rocky planet that's formed itself as a rockiness.
Okay.
So these are like super, super dense, big rocks that are probably not very good for life.
Right. And is that because... the much larger hot Jupiter that was around them, the sort of the pressure at the core from all the stuff around it has just really condensed
crushed it all the way down.
Yeah,
so they're super dense.
Right. So you're left
material.
with this incredibly
So you have
dense
huge gravity
lump.
and it's just they're all a bit weird, and they're quite close to their host stars as well.
That doesn't sound fun.
That's an example of a bigger rocky planet that we're not really interested in.
Sure. But in terms of rocky planets that form in similar ways to the rocky planets that we know and love, like us, Venus, Mars.
Yep.
Is there like a maximum size that they tend to be?
Well, not really, because we sort of, when we started classifying all our exoplanets, our solar system didn't give us some very good pinpoints, I would say.
Right.
Because you've got...
Again, N of 1 of each of them.
Yeah, we've got the Earth, which is Earth, and then you've got the next biggest object, which is Neptune.
It's quite a jump.
It's quite a jump.
Yeah.
So there's a lot of things that exist in the exoplanet discoveries between those two. With some of them we call mini Neptunes, some of them we call super Earths.
They sort of overlap in the middle, I would imagine. That's
overlapping
Venn
around
diagram.
about 3-ish Earth masses. Maybe there's a line between those two, something like that.
Correct me if I'm wrong, Neptune's gas giant.
Yes.
Right? Yes. But so a mini Neptune, at some point it segues, maybe, from gas giant, mini Neptune, super Earth.
Yeah.
There's a transition period.
And remember that when we talk about these things, what we are measuring from our observations of these exoplanets is we're not seeing necessarily, are you a gas giant, are you a rocky thing? Because we don't have that level of detail. It's a very common I guess, assumption that we're just going out and taking pictures of these exoplanets that are as good as the pictures we have of Neptune or other planets in our solar system.
We're not seeing them.
No.
We're seeing their effect.
Yeah.
We're measuring that they're there by what they do to things nearby.
So the information is rather limited, and typically we really only got things like mass and radius.
Mm-hmm.
So mass and radius are quite useful because you can calculate the density. But does that density, that's the bulk density, it's the overall density of the planet. Does that mean that you've got a planet with a really kind of big rocky core and then a lot of ocean and then a thick atmosphere? Or is it a rocky thing with a big rocky thing with a really thin atmosphere? Both of those examples work with the maths, right? So we don't always have any further information to be able to distinguish those two.
Wouldn't it be really weird if one day we do get to another exoplanet system and we get out there and they go, oh no, you guys are the weird ones. Our planets are all made out of cake. And we never knew.
Yeah.
It's possible.
Cheese would be better though, wouldn't it?
Yeah. Anyway, yes. So
yes. Earth twins, right, coming back all the way back to Earth twins. So small rocky worlds in the habitable zone. And there's lots of other things you can say that you want to define in terms of habitability, but those are basically where we need to start the search, I think.
Sure.
So there is a catalogue which is called the Habitable Worlds Catalogue, and this is comprised out of the group who are at Arecibo Observatory, actually. So they take the exoplanets that we've all seen and they pull out, basically, these are the ones that are rocky worlds in the habitable zone. So these are probably our top candidates for Earth twins, if you like. So they make a list. Now they've got about, from remember, a pool of currently
6,000?
Around 6,000.
Yeah, I don't like the expression on your face as you're leading up to this.
They've got around 70 candidates.
That's bigger than I feared. I thought you were going to say 7. And then you said 17? No, 70.
Okay. You can break that down a little bit. About 40 of those are actually water, icy, mini Neptune-y things that probably aren't as good, really.
Okay, but let's not completely sideline them. Let's hang on to them for a minute.
They're in there.
At least.
But really, the ones that are the best, with about 30-odd rocky planets. And from those 30-odd, I picked up 3-ish. That are probably like the favourite targets. Okay.
So what you're telling me is we're not exactly spoiled for choice, but at least we have something to look at and to play with. We can look at this.
And there's huge variation in those 30 about how much we know about them too. Some of them are quite close, and I'll mention one that's very, very close. And that's good because it's easier to get data on it. Some of them are a bit far away. Some of them are microlensing exoplanets, so we're probably never going to see them again.
Damn it.
So
that's a bit hard.
Yeah, you're a bit stuck with those. Anyway, let's got 3-ish. Should we just have a quick run through?
Let's have a look at those. If those are our best shot, then let's have a look.
Yeah. Well, let's start with probably the most famous exoplanets.
Do these ones actually have names, or do they have Cody names?
Some of them do, but I didn't write down all their names.
Okay.
But I like the stars. The first one...
You being a star person.
I know, I'm too obsessed with the stars. The first one that many people will have heard of is the TRAPPIST-1 system.
We've talked about TRAPPIST.
Super
before.
famous.
Yeah.
7 Earth-sized planets, all in one system. Very nice.
Okay.
3 of them are in the habitable zone, depending on your favourite definition of habitable zone. But broadly, we agree there's 3. Planets E, F, and G. And nicely, the whole system is only about 40 light years away. So
that's fairly close by
on the grand
sort of
scheme of things.
Standards, yeah.
Yeah. The problem is that we don't really know much about these planets, despite them being, fairly well established in the literature now and fairly well studied. There's not really much of a hint that any of them have atmospheres. Which is kind of the next step you'd like to go along. If you've got your small rocky planet going in the habitable zone, next step would be find an atmosphere, because when you've got an atmosphere, you can even start measuring what the atmosphere is made up of, which is even more exciting. Doesn't really look like E, F, and G have atmospheres. At least we've not seen them. We've tried.
Doesn't mean they don't, but we got nothing yet.
No, even from JWST. And the problem is that they're going around one of these dwarf M stars.
Which we remember from last time as they're rough.
Yeah, they're a bit active. That can strip atmospheres from planets nearby. So
active in the sense that they're like our sun has been a bit active over the last year or so. It's come up to the top.
It's a few orders of magnitude more than that.
Spitting out a lot of stuff. And worse.
Yeah. Big flares, lots of radiation that tends to break apart atmospheres and strip them off.
Which is, from a life point of view, not great.
No.
Great.
So
points to TRAPPIST, right, for an overabundance of rocky planets. A high achievement there. Well done. 3 in the right kind of zone.
Yep.
Right kind of size, right kind of distance, wrong kind of star, maybe no atmosphere.
So,
right.
Oh, well. But, that's still one of the top 3. So.
These are the good ones.
On the top 3 systems.
Good. Next.
The next one, which has been in and out of the news quite recently, Proxima Centaurus b. So Proxima Centaurus is the closest star that we have to the sun.
Hence the name.
Yeah. Nice and close. Only about 3 and a bit light years away. So the planet that's going around here, we don't know exactly how big it is, but the smallest it could possibly be and fit the data is about just over 1 and a bit Earth masses.
Okay.
So about 1.1,
sure.
1.2.
So that's pretty close.
Earth masses, yeah. It's going around in the same orbital distance as our friend Dimidium. So...
Oh, like really close.
1/8 of the orbit of Mercury.
And what's this star like?
Well, on the bright side, the star's really cool.
Good.
Yeah.
Good, because you don't want to be that close to something really, really hot.
So the surface temperature, the surface temperature of the star is only about 3,000 Kelvin, whereas ours is 5,800, something like that.
But that's 1/8 the distance to Mercury. And we already know that Mercury is just, a blasted lump of rock.
Yeah.
So even if the star's quite cool, it's still several thousand degrees. And you're 1/8 distance. That's just...
And it's a really active star.
Oh, okay.
And it's got flares. It's been known to be active, the star. It's got flares. And we've not seen any atmosphere on this planet yet.
So I don't think that sounds very promising.
Well,
so
I can try again.
Yeah, next.
Last one.
Number 3.
Last one. You'll love the name of this one. LHS 1140b.
Very nice.
Yeah,
very nice.
Good one. This one's a bit bigger. This is actually a super Earth, so it's coming in 6.6 Earth masses.
Okay, and how much bigger is Neptune? Like when do you?
Oh, more than that. I didn't write down what Neptune's mass is and Earth mass is.
But we're definitely we're in super Earth territory. We're not up into gas giant territory.
There's a blur, right? The Venn diagram does overlap at some point in these categories, and I don't know whether you draw the hard line between the two, but anyway. But the good news about this planet is that although it's more massive than Earth by 6 and a bit times, it's actually only 1.6 times the radius.
Okay.
So it's not like big volumetrically like Neptune. It's smallish and very dense.
I was about to say, so, if you took the stuff that Earth's made of and you made it 6 times the mass, because of the way volume works, that doesn't mean that the radius is 6 times more.
No.
Because mass is it's a number and dimension is tripled when you get into volumes, but it would be more than that.
Yes.
So this is a very dense object,
which
means that the gravity around it will be stronger.
It will be, yeah. Now this is actually possibly a good thing for this planet.
Okay.
Because once again, it's going around one of these M dwarf stars, right? Now it's not quite as close as Proxima Cem. In fact, it's about double the distance, so only a quarter of Mercury's orbit.
Not quite as close, but still close to a M dwarf nasty star.
But if it's this dense, there's a good chance that if it has had an atmosphere in the past, or if it was born with an atmosphere or collated an atmosphere along the way, it could hold on to that atmosphere.
Right. Because the denser it is, the more grip the more attraction it's got for anything currently sitting around its surface. So it can hang on to an atmosphere
So it may well have a very thick atmosphere.
under difficult circumstances.
Yeah. So that's kind of possibly quite a good thing.
Okay.
Another good thing is actually the star is on the quieter end of the spectrum for these M dwarfs.
Is that a relative spectrum? I mean,
Well,
quieter end of a toddler having a tantrum?
A little bit through gritted teeth, because my students like to point this out when they say, but this one's really habitable. The star's much quieter. We've only been observing it for 50 years or, maximum, something like that, right? Stellar lifetimes are long. Maybe it's just in a little bit of a quiet period. So I'll try not to be too skeptical, but maybe it's a good thing that this particular star is a little...
Look, in comparison to the other two that you mentioned, this one's looking great. Like, all my money's on this one currently.
You're booking your transportation on the rocket already.
Yeah.
So those are my three. I mean, I don't really mean to sort of say, look, these ones, oh, they're terrible. Oh, look, there's another one. Oh, they're terrible.
You're breaking my
Loads
heart.
of people get really excited about these. And maybe that just means that we just have to be a bit more open-minded about what life can do, if that makes sense, what life can cope with.
Right. Okay. So, I mean, if we're finding a lack of earthy planets in the right place around the right stars, it makes sense to then start pushing out at the envelope of, well, maybe we could start including some of these planets over here, because maybe life's a bit more robust and a bit more inventive than that.
Because I think it's not too much of a step to go from, okay, these planets, if, say, the first two, they didn't have atmospheres. But that doesn't mean that life couldn't have done something underground. Maybe.
Sure.
In a underground subterranean ocean or something like that. For the last one, similarly, the atmosphere could be quite helpful in protecting, what life might be on there. Or, life might have formed in a slightly different place. Maybe there's a moon.
Sure.
I mean, we could go all sorts of different places with this. And by the time you start expanding out those ideas, then you might as well include other exoplanets themselves that are outside those initial boundary conditions, but might be in some ways even better for life than an Earth twin.
Sure. Okay. So have we got, any data or any examples of planets which are in this sort of next ring of the onion out, which is, all right, we've gone through that list of earthy ones, not looking great currently. So what else have we got?
So a group of exoplanets, or a class of exoplanets that are getting a lot of people very excited, especially recently, are called Hycean worlds.
Hycean worlds. What's an Hycean world when you look at it?
A Hycean world is an ocean world, a water world, that has a very hydrogen-rich atmosphere on top of it. So the whole planet has a liquid ocean, and then it's got a big atmosphere on top of it, predominantly hydrogen.
And always hydrogen? Like, is that how that works? Is it just...
Well, it's linked to the fact you've got so much water as well.
Okay.
Like there's always an interplay between the ocean and the atmosphere. But
so
it
that's
seems,
how that would turn out.
Yeah.
Right.
And these are kind of in the range of 2 to 3 times the radius of Earth, so a bit bigger, and they can go up to maybe 10 times the mass of Earth, because now you might have a much bigger rocky core that then has a sort of deepish ocean on top.
Okay.
It sounds quite interesting.
It does sound. And look, we've got a lot of life in the oceans on our planet.
Yeah.
Why not? That's presumably kind of where it all started.
Yeah. And water can move, and water can interact with the rocks underneath, and it can interact with gases up above. So you can get lots of churning around of stuff between the rocks and the atmosphere. So you're moving material around. You've got energy processes. You might have geothermal processes. There's all sorts of things that can kind of happen in this.
Sounds good. You're selling me on it. What are they called?
Hycean worlds, okay. Yeah. So then the big thing is that in those atmospheres, although they're hydrogen rich, you might also find lots of organic compounds, methane, ammonia, and I'm going to say it, dimethyl sulfide.
Dimethyl sulfide. Okay, you're saying that with a grin on your face. Remind me, dimethyl sulfide.
So cast your mind all the way back to April 2025, just a few months ago. The big breaking news that came out was that we have detected dimethyl sulfide on an exoplanet.
All of the headlines were, oh my God, life.
And pictures of aliens with big eyes
Yes.
or flying fish
Yes.
because this is a water world.
Yes, because and all the astronomers just went, no, look, step back. I mean, thank you for all the attention, but no, that's not what we're saying.
Well-
but why is that?
Well, dimethyl sulfide on Earth. Well, there's two things about dimethyl sulfide. First of all, it's not a very long-lived molecule. So sunlight, starlight will break it up. It will need replenishment. So if we've detected it, it's being depleted in its local environment. So it must also being produced.
Something's making it.
So something's making it.
Right.
There's something. Otherwise, it would just all go away.
Life.
Well, yeah, a little bit. On Earth, the only processes that are known to produce significant amounts of dimethyl sulfide are marine life.
Right. Hence the excitement.
Yes.
But there's an enormous asterisk next to that, which is that's just our experience. And, life is very clever. Evolution is very clever. But, chemistry is pretty clever too. Chemistry can come up with all sorts of ways.
You're sounding a lot like me, Chris. I thought you were the optimistic one in this.
I am. I'm just
this
trying to sort of
podcast.
anchor us here. I think this discovery got way, way more breathless OMG life coverage. We don't need to add to that. So I think our role here is, yeah, okay, good. That's really exciting. But let's just not get ahead of ourselves. It could just be chemistry.
It could. Let's come back to this. So the planet that was detected on was called K2-18b. Now, probably one of the most famous life-like exoplanets that we have. So this particular one is 8.6 times the mass of the Earth, twice 2.6 times the radius. It goes around a star in a month or so. The star is an M dwarf, but it's a little bit on the hotter end of M dwarf, so it's not quite as nasty as the cooler ones. But the nice thing is that what's calculated to be the equilibrium temperature. I'll come back to what equilibrium means.
Okay, yeah.
But the equilibrium temperature sounds like a very nice, balmy 23 degrees Celsius.
That sounds very comfortable. That sounds like that's a nice day for a swim in this big ocean with its hydrogen atmosphere. But yeah, sure.
So the problem with equilibrium temperatures is that is what temperature you would be if you didn't have any atmosphere and you didn't have any, or you make some random assumption about how shiny you are.
Right.
And those things are, which is called albedo. Those things are important because how shiny you are, how reflective you are, changes how hot you are. If you're very reflective, you're not going to be very hot. If you're not very reflective, you're going to absorb all the heat. It's like wearing a black shirt on a summer's day.
Yeah, or being in a black car.
Yeah.
Don't do that in very hot places.
Yeah. And same with the atmosphere. The atmosphere can be like a nice warm blanket that keeps you nice and snug, or if it's very thin, it can just let all that heat escape, and then you're done.
Okay. So what you're saying is it's 23 degrees adjusted up or down by small or large amounts, depending on
Probably
what
at
the
least
planet's
100 degrees.
actually like. So 23 plus or minus 100 could be stupidly cold or ridiculously hot, but 23.
Yeah.
Sounds really nice. Okay.
You're booking your holiday now. Yeah. Okay, so this was April 2025. We weren't recording at the time, which was a shame because we would have made it. We would have told them.
We would have told them, but here we are now.
Yeah, but so we're going to tell them now.
Yeah.
But I can actually say that there are other people who have told them by this point.
Well, there are other pundits than us. Who'd have thought?
Who'd have thought? The first thing was that this was a detection at the 3 sigma level. That might not mean much to most people.
Explain that to the masses.
It means that it is, so a sigma is called a standard deviation. It means we have a gold standard in science that for something to be counted as being a new detection, it needs to be 5 sigma. That means it's 5 standard deviations away from the average or what we would expect to have happened. Basically, it's so far away that statistically almost impossible that this could be a random error.
Right. And sorry, specifically, what measurement are we talking about here that is 3 sigma? What's the
detection? So the fact that
detection of
the dimethyl sulfide.
Right. Okay.
Dimethyl sulfide is there.
Okay. So to translate this 3 sigma, what we're basically saying is, let's assume there is no dimethyl sulfur, right? None. That would be sitting right there at 0. And we've found a result which says there is some. Well, how big is that result? Well, it's 3 standard deviations. It's 3 good like hand spans away from the null result, away from the there's nothing there is, well, maybe it's there, or maybe it's there. It actually really seems like it's there to the 3 standard deviation limit.
I think you're getting up into the 90%-ish at 3 standard.
And at that point, you're saying there's a very small chance that we're wrong. But the gold standard in at least many parts of science, it depends on who you're talking to, is 5 sigma, which is really small. Like I swear to you, we did not mess this up. Like either we've just been hit by the biggest coincidence in the world, or it really is what we say it is.
Yeah.
Okay, so 3 is good, but it still leaves a bit of wiggle room for, look, coincidences happen, right?
Yeah.
It might not be there in as much as you think.
And that's assuming that, well, that number takes into account that you have made all the correct assumptions in the way that you have analysed the data as well.
Sure.
So,
of which I'm imagining there are a few.
Yeah, I mean, this is coming from transmission spectroscopy, from JWST. Basically, we're looking at tiny little bumps and wiggles. I think we've talked about some of these transmission spectra. I feel terrible because I do high-resolution spectroscopy of stars. I know what spectra can look like, and really, when you've got lots of photons, basically, you've got lots of information coming from other stars. These spectra don't look that great to me.
Look, you're not wanting to dump on these guys, but this is hard.
It's not my area, but...
this is hard. Yeah,
I wouldn't like to be drawing too much out of some of these spectra.
And to be clear, I mean, you're talking about transmission spectra. So this is light from the star going through the atmosphere, whatever that is, of the planet. And we are detecting tiny, tiny changes in that spectrum from the original star, which we are then inferring details about the atmosphere. Yeah. And one of those inferences is, hey, something that we associate with life here on Earth. But that's really hard.
Yeah. So there's a few steps along the way. So there's, first of all, is the detection there. And, well, actually there's been a paper come out that came out in July 2025, so just a couple of months ago, where NASA reanalyzed the same data and actually said, we're not actually sure we haven't not conclusively seen dimethyl sulfide, actually. That was the conclusion of that paper.
Wind it back.
And it is because it's hard. You've got lots of different chemical elements that produce signatures in spectra. So it's not always easy to pick out which molecule, which element is doing what, and to what level, and how much of noise, and how much they're hard. It's not easy.
I mean, the fingerprint of each chemical species in existence is reasonably straightforward in the sense that it's a bunch of lines in the spectrum, in the color spectrum. But when you and some of those can be very complicated, but when you put a bunch of them together, and then you add in things like it's moving.
Well, it's even worse because these are molecules.
And these are molecules.
Molecules have really big, wide bands.
Of course.
Because they vibrate and they do all sorts of...
Yeah. So that then suddenly becomes is that a fingerprint of a moose or a mouse? It's really hard. I'm not sure that my analogies are very good today. But, it's really hard.
But they kind of sound nice. They rhyme together.
I think you could probably tell the fingerprint of a moose from a mouse. That's a bad example.
Not from maybe tens of parsecs.
True. That's a fair point. Yeah.
So the detection is actually a little bit inconclusive at the moment now. Also, there's been a lot of work that's been published since that says actually you can produce dimethyl sulfide from abiotic processes.
Damn it.
So it's not kind of the silver bullet that we were looking for.
Chemistry.
I know. So sorry. Mm-hmm. If we had recorded in April 2025, I think we'd just be saying, we told you so. But
we'll do that now anyway.
Yeah,
we'll do that now anyway.
Why not? Yeah. But so unfortunately that one doesn't look like it's going to be life-bearing, despite the hype on the news.
That's a shame.
And shame on you, Daily Mail, for those AI-generated images of flying fish.
Do you know what? I don't think the Daily Mail cares. I think they got their paper sales out of it. They're fine. They got their subscription. That's all good. But each one of these examples says to me, and this is a theme that has come up many times on this podcast, which is a lot of the hype comes out of, OMG, we have discovered X, and the astronomers maybe bask in a bit of that publicity glow, or run away from it, depending on the astronomer. But ultimately, when it all settles down and shakes out, what you're really talking about is we are learning more about what the possibilities are. And each of these is a test case. What can we find out? Can we narrow it down? Can we narrow that parameter space? And so even if we don't end up with, special molecule on planet X, we have measured planet X and figured out a hell of a lot about trying to find special molecule.
Yeah. So Hycean worlds, I think, still are quite good in terms of possibilities. I'm not going to say that just because this one didn't have dimethyl sulfide that we should throw the baby out with the bathwater.
Sure, it's still a great place to go and have a look.
Exactly. But there's one more that I thought was worth mentioning, and that is the icy ocean planets. Now, I'm really sad because these planets don't have a cute name, like the Hycean worlds or the hot Jupiters or the
super Earths.
Yeah.
They're just icy
ocean planets, and even that's not very particularly official.
I mean, it kind of sounds cool.
I think it does. So, yeah.
So
I would put this challenge out to the listeners to say, come up with a nice class name for our icy ocean worlds.
We've got to be able to do better than that. Yeah, write into us at Syzygy.
Yeah.
So describe an icy ocean planet to us. I mean, are we talking a layer of ice over an ocean?
That's pretty much it. Okay, yeah. So you've got some kind of core, likely it'd be a solid core somewhere down there, possibly a very deep ocean, and then possibly a very thick icy crust on top. Well, it had to be fairly thick to survive, I think.
So these things are presumably further out because they have to be colder, because they have to be icy? That's the idea?
Yeah. But because you've got the liquid ocean underneath the surface, actually you're not constrained anymore to the habitable zone because the heating for this ocean can come from other sources. For example, the geothermal energy of being from the underneath the rocky bit, or you've just got a bit more play, I guess, in your habitable zone.
Sure, because of course planets can have sources of energy, sources of heat that aren't the star, that are actually internal to them. Earth is one of them.
We believe Mars used to have a lot of this, and the Mars has subsequently cooled and become colder. But in the past, it could have been a lot warmer just from its own internal energy.
Okay, all right. Do we know of any of these? Like, is this a completely hypothetical, or
we've got one quite good one?
Yeah,
you're not going to like the name.
Okay,
it's Ogle OGLE / 2005 BLG - 390 LB.
Wow, even by astronomical standards, that's pretty rubbish. Yeah.
It's got a nickname. It's called Hoth.
Hoth, as in Star Wars, as in Frozen Planet Star Wars.
Yep.
But, I mean, as far as I remember, they never at least described an underwater ocean or an under ice ocean, I mean, in Star Wars. So, sure, okay, let's go with Hoth.
But something would have had to freeze, right? I don't know.
Yeah. Well, okay. Yep.
I don't know. I'm not very read up, I'm afraid, on the evolutionary history of icy ocean worlds yet.
Okay. All right.
Anyway, this one's a 5.5 Earth mass planet. It's going around an M dwarf, but it's going out much, much further away from these other little sort of planets that were nestled nicely snug and close.
All of
into
these
their
planets
stars.
we've been talking about have been dwarfs. Is that because, if I remember correctly, there's a lot of them? Dwarfs are the most common.
There's a lot of them, and also planets are easier to detect around dwarfs because they have higher effects on the star.
Right. The smaller the star is, the more it's going to wobble.
Or more light is going to be blocked. Yeah.
Okay, that makes sense.
So, yeah. So this one's about 2.6 astronomical units, so 2.5 times the distance from Earth to the Sun, but a much cooler star. So this is a very, very cold.
Yeah. How many astronomical units is Mars?
1.7, I think, something like
so
that.
So further out than Mars.
Yep.
From a smaller, cooler star.
Yeah.
Okay.
Yeah. So the equilibrium temperature is around minus 220 degrees Celsius.
Okay.
It's chilly. But if you've got geothermal heating and you've got, therefore, some kind of lukewarm, watery ocean underneath, then why not?
Sure, it could happen. But how do we know anything about this one? I mean, couldn't it just be a lump of rock? Like, why are we calling it Hoth?
Well, because it looks like an icy world from Star Wars.
But how do we know?
I'm out of data, I'm afraid, Chris. What do you want? I'm afraid we haven't sent drills to go down underneath the ice shelf.
All right.
Yeah.
I will shelve my skepticism and just say, sure. Oh, I see. Well, why not?
I mean, it's just really an example of other environments that could host life that, okay, in this case, would it be detectable? It's a bit, yeah, okay, I get your point. But, let's just keep our minds open.
Let's just keep an open mind.
Or we could keep our minds open for, here we go, is my off the top of my head list that I direct.
Hit me with another one. Yep.
Life could be floating in the atmospheres of Jupiter, Saturn-like planets.
Sure.
It could be swimming around in pools of lava on lava worlds.
Yes.
It could be hiding in the rocks and twilight zones of planets that are locked to their host star. So where you've got a hot side and a cool side.
And they're just nestled around the border there.
The transition zone.
Not too hot, not too cold.
Living there.
So they've got their own Goldilocks zone on their own planet.
Yeah. They could be living on rogue planets, so planets without stars at all, so long as
wandering through the universe.
Yeah. Moons of exoplanets.
Could happen.
If the planet's not nice, maybe it's got a nice moon. You could go live on.
Does feel to me a little bit like we're just getting a bit speculative now. So it could be anywhere. Yeah, but I guess all you can do is start saying, what can we conceive of, and start narrowing things down. It's definitely not this. We're not going to find it on, what was that first planet that we talked about?
The medium.
Yeah, we're not. I think we can all agree that's not going to happen. A hot Jupiter that close to a horrific star. Let's just say no to that one.
Yeah, okay. I think we should say
get rid of
no.
all of those.
Yep.
And we've talked about the earthy ones. There's not that many of those.
Nope.
Challenging. So let's just where else? Where could it be?
Well, and it's like we don't have anything close to hand that we could be looking at that might look like some of these places.
You're saying that in a way that makes me kind of feel like maybe
it's a very forced transition, Chris.
Maybe we do.
Maybe we do.
Maybe we do.
We've got rocky things in our solar system that are a little bit hotter than Earth with thick atmospheres.
Nice segue.
Oh, we go.
Rather than exoplanets, we have an N of 1 currently in the universe. We have an N of 1 in our solar system. But it's much easier to look in our solar system, I would think. We could actually conceivably go to some of these places.
Well, indeed. And we do.
Yeah. So what are the possibilities in our own backyard?
So, the Earth twins, let's go back to them. So you could look at, we've got a couple of other Earth twins in our solar system.
Venus and Mars.
Exactly. One is a little bit too hot, one's a little bit too cold, but have had different evolutionary histories. Obviously, we're quite focused on Mars with all the little rovers running around looking for signs of, if we're honest, probably extinct life. But
wasn't there something very recently where there was a rock that a rover found and went, oh, look, that could be interesting. And again, the world just went nuts. We've just found we found it. Just give us a minute. Let's just take a look at what we found. But it could be. Yeah. It could be.
Yeah. So Mars is obviously super interesting. But even Venus, we've had phosphine on Venus. We're not going to go down that road again right now. But, it's not completely
much
ruled
easier
out.
To drive around on Mars than it is on Venus. Venus is rough.
Yeah.
Not in the rocky sense, just in that's a hell of a place.
But then if you come back to these icy ocean planets, we've got analogies of those in our solar system.
Whereabouts?
And about some of our moons of our gas giants.
As you were saying, moons before, could be moons. I mean, just because you've got a bloody great gas giant doesn't mean that you're only forced to look for life there. They've got lots of moons. Lots and lots of moons.
And some famous ones like Europa, which is the icy moon of Jupiter, or Enceladus from Saturn. So,
and some of these, we know they have activity, right? We know that they've got underground energy like we do through volcanism. They have as well. Yeah,
because their surface ice is all cracking, which is showing that it's moving. Why would it be moving? Well, it's got some tidal heating.
There's stuff happening under there. And if there's stuff happening, there's energy. And if there's energy is important. You need a bit of energy. Could be.
And we've even got, we didn't really talk about this as a possibility for exoplanets, but people still get excited about Titan.
What's going on Titan?
So we've got lots of pools of methane lakes and things like that. Lots of organic chemistry, basically. All the organic chemistry you could want in one place.
It's all there. All the ingredients are there. Like when they take away the gingham cloth on Bake Off. So here's all your ingredients for life. your signature challenge today is make life. But Titan, does it it should be cold because it's a long way away. So the fact that we have lakes, does that mean it also has
again,
activity,
it's got tidal heating from Saturn.
Right?
Right?
Oh, of course, yes, of course. I wasn't
Saturn.
even thinking of
These
that.
big masses give you lots of gravitational energy.
Yeah.
So, I mean, we sent a probe, right? Huygens probe.
Mm-hmm.
So that's still, it's an interesting place, and we should find out more because, all of these places these are our top places. There are still people who are interested in looking at asteroids and seeing if there's anything exciting going on the inside of asteroids. Comets, icy snowballs, are they just flinging life around the solar system?
Yeah, I mean, isn't there all sorts of theories, and I don't know how well entertained they are. Entertaining, yes, but how scientifically entertained they are. That life on Earth, there are those who say it had to have come from elsewhere. That it was brought by a comet or an asteroid or something. To me, that kind of feels like you're just kicking the can down the road. Like, where did that come from? Surely we should just assume that it started here on Earth and go with that. But regardless, it's not a crazy theory. Doesn't mean
it's
right.
called panspermia, that life might sort of hop between places.
Yeah.
My understanding is actually that's sort of fallen a little bit to the out of favor side of explanations, and more people are thinking, well, if there is life on some of these sort of top candidates in our solar system, it probably independently evolved there, which is weird to think about.
Sure.
That life will just start popping up and bubbles everywhere.
Yeah, but I mean, I guess there's a couple of possibilities here, aren't there?
Yeah.
One is that life happens incredibly rarely, and we're just it. The other is that life happens not so incredibly rarely, and in which case you would expect to find it in a bunch of places where it can. Just a roll of the dice, right?
I guess there's a third possibility that we're actually really rubbish at finding life.
There's that too. Yeah. And that could be both of those, right? That it's incredibly rare and we're rubbish at finding it. No chance. It's not incredibly rare and we're rubbish at finding it. We have a hope. There's, depends how rare it is. We'll just keep looking. Of the places within our solar system, have we tried to find life, explicitly looking? I know we are on Mars in the sense of little rover running around going, pointing at rocks, and sampling them. And, that's a very, very slow process. But the moons, what can we do in order to try to figure out, what would you have to do to try to figure that out?
I think this is a good place to say, let's find out when we do a deeper dive into the places that life could live on our solar system.
Deeper dive, figuratively and literally?
Possibly.
Excellent.
Yeah. And go hunting for some solar system sanctuary.
Very nice. Is that our next episode?
That's our next episode.
Fantastic. I love a good segue. All right, Emily, look, you've left us there with a tantalizing little tease for next time, which is, if we're going to look for life in the universe, you may as well look in your backyard. It's an easier place to go and dig up stuff. So let's go and find out just how hard or easy that is next time around.
Yeah, because remember that exoplanets are really weird. And if exoplanets can be really weird, maybe we need to think a bit more weirdly about the things that are closer to home as well.
Yeah. And maybe learn something that'll help us with the weird exoplanets, or maybe just go and find some life in our backyard. That'd be easier.
Then we can give up on this exoplanet nonsense,
Well,
right?
I mean, I think the exoplanet scientists would probably have issue with that, but it certainly would. I think if we found other life in our solar system, even though it might be just an N of 2 now, that's N of 2 here, right here. Forgetting about the fact that we're in a galaxy, in a universe of galaxies. That's an N of 2 in our backyard. Surely.
It changes the statistical likelihood
really
of life
does.
being everywhere, doesn't it?
It really does, right? That would be amazing. I still contend that I'm not entirely sure how it would change our worldview, psychologically and philosophically, I'm not sure that many people would walk around doing their lives any differently if we found life
Which is
on
a
Mars.
shame, but...
Yeah, but I think scientifically it's a hell of a question.
Yeah.
Anyway, listen, we've put a couple of questions out there into the world, and I'll be interested to see if anyone comes back with a new category name for what was the...
Icy ocean.
The icy ocean worlds,
planets.
right? Let us know what you think. And didn't we ask another one? Wasn't there another question that we had in today's...
If you're a biologist and you can correct all my poor
Oh,
biology.
that's what it was. Yes.
Very open to...
If your research specialty actually allows you to opine, then please do write in and put us
Otherwise,
put us
I'm just
right.
going to have to go find another biologist friend to get some of this stuff because...
Yeah, or you and I will just keep making stuff up. I mean, that's, it hasn't stopped us before. Listen, if people wanted to write in, Emily, how would they do that? How do they get in contact with us?
Well, we don't have many carrier pigeon hubs here, I'm
We don't,
afraid.
no.
So you're going to have to go to the website,
Yep.
which is syzygy.fm, syzygy.fm.
That's right. What do they find when they go there?
There's a box. I'm drawing a rectangle, actually. It's a
Right,
rectangular box, and you put the thing that you want to say to us, and you put your email address, and you push go.
I think we can probably assume that people have used the internet
Okay.
before. Yeah. Go to our website. What are we even doing? Go to our website and you can fill in the form and send it our way. While you're there, you can listen back to the 120 plus episodes that have come before, all the way back to 2018, through the very, very long season 1, the somewhat shorter season 2, and here we are in season 3. You can also go and visit the Great Wall of Thanks, which is our way of saying a big, heartfelt syzygy thank you to the people who make this all possible. From the lovely people here at the University of York that, I mean, let's face it, employ Emily and allow us to sit around the table here
Very
and witter on. But also all the people who go to patreon.com/syzygypod and support us financially. And you too can be one of those people. For just a couple of pounds a month, you can help us to keep the electrons flowing through this beautiful thing we call the Syzygy podcast. But the most important thing you can do is just tell everyone that you know that there are these crazy people who like talking about life on other really weird worlds around the universe. And maybe they too will find it a fascinating thing to listen to of a weekly basis. But otherwise, I mean, we know where we're going next, Emily. We're going to our backyard and we're going to dig up some life.
We are.
We are. So join us in a week or so's time. We'll
Yeah.
catch up with you soon.
See you later.
See you later, everybody. Bye, Emily.